পড়া আছে।
ও ঠিক আছে।
প্রিয় শিক্ষার্থীবৃন্দ, সহকর্মীবৃন্দ এবং যে সকল দর্শক এই মুহূর্তে ফেসবুক লাইভ এবং ইউটিউব লাইভের মাধ্যমে আমাদের এই ইন্টারন্যাশনাল ফিজিক্স ওয়েবিনারটি দেখছেন, আপনাদের সকলকে আমাদের ফেসবুক পেজ এবং ইউটিউব চ্যানেলে স্বাগতম। শুভ সন্ধ্যা সবাইকে। এবং আজকে আমাদের পাবনা বিজ্ঞান ও প্রযুক্তি বিশ্ববিদ্যালয়ের জন্মদিন। আজকে আমরা 13 বছর পার করে 14 বছরে পদার্পণ করলাম। তো আমাদের প্রতিষ্ঠাকালীন সময় থেকে যারা এই পাবনা বিজ্ঞান ও প্রযুক্তি বিশ্ববিদ্যালয়ে গড়ার পিছে এবং আজকে এই এত দূর আসতে যাদের অক্লান্ত পরিশ্রমে এত দূর এসেছে, তাদের সকলের কাছে আসলে আমরা কৃতজ্ঞতা প্রকাশ করছি এবং সকলকে ধন্যবাদ জানাচ্ছি। আপনাদের সকলের অক্লান্ত পরিশ্রমে আজকে আমাদের বিশ্ববিদ্যালয় একটা জায়গায় দাঁড়িয়ে আছে। আমরা আশা করব এই বিশ্ববিদ্যালয়টা এমন একটা জায়গায় যাক যেটা নিয়ে আমরা সবাই গর্ব করতে পারি। আমাদের ছোট্ট প্রয়াস, আমরা পাবনা বিজ্ঞান ও প্রযুক্তি বিশ্ববিদ্যালয়ের পদার্থবিজ্ঞান বিভাগ গত জুন মাস 2020 সাল থেকে আমরা এই করোনাকালীন প্যান্ডামিকের মধ্যে আমরা আমাদের ছাত্রছাত্রীদেরকে পড়াশোনার মধ্যে ধরে রাখা এবং বিজ্ঞানের প্রতি একটা আকর্ষণ তৈরি করা বা বিজ্ঞানের গবেষণা নিয়ে তাদের মধ্যে একটা তাদেরকে জানানোর একটা উদ্যোগ আমরা গ্রহণ করেছিলাম। আমরা ইন্টারন্যাশনাল ফিজিক্স ওয়েবিনার আয়োজন করে যাচ্ছি। আমরা ইতিমধ্যে 183টা ইন্টারন্যাশনাল ফিজিক্স ওয়েবিনার সফলতার সহিত আয়োজন করতে সক্ষম হয়েছি। আজকে আমাদের 184তম ইন্টারন্যাশনাল ফিজিক্স ওয়েবিনার। এবং আপনারা ইতিমধ্যে জেনেছেন যে এই আয়োজনে আমাদের সাথে 2 জন নোবেল বিজয়ী পদার্থবিজ্ঞানীও ছিল। তো আজকে আমাদের সাথে উপস্থিত হয়েছেন আমাদের শ্রদ্ধেয় স্যার ডক্টর প্রফেসর অ্যাসোসিয়েট প্রফেসর হিসেবে কর্মরত আছেন মোহাম্মদ হুদা স্যার। এবং আমাদের আজকের এই বিশেষ ওয়েবিনারে আমাদের সাথে আছেন পাবনা বিজ্ঞান ও প্রযুক্তি বিশ্ববিদ্যালয়ের পদার্থবিজ্ঞান বিভাগের চেয়ারম্যান প্রফেসর ডক্টর খায়রুল আলম স্যার। এবং আমাদের সাথে আরো একজন আমাদের শ্রদ্ধেয় স্যার ডক্টর শেখ রাসেল আল আহমেদ স্যারও সংযুক্ত হয়েছেন। তিনি ইসি ডিপার্টমেন্টের অ্যাসোসিয়েট প্রফেসর এবং প্রাক্তন ডিন ইঞ্জিনিয়ারিং ফ্যাকাল্টি। তো আমি সবাইকে স্বাগতম জানাচ্ছি এবং প্রথমেই আমি আমাদের আজকের অনুষ্ঠানের গেস্টদেরকে কিছু বলার জন্য অনুরোধ করব। খায়রুল স্যার এবং শেখ রাসেল আল আহমেদ স্যারকে আমরা প্রথমেই তাদের কাছ থেকে শুনবো এবং তারপরে আমরা চলে যাব আমাদের শ্রদ্ধেয় মোহাম্মদ হুদা স্যারের কাছে। এবং যেহেতু আজকে পরিবেশ দিবস, আমরা আমাদের আজকের যে বিষয় সেই বিষয়ের সাথে একটু পরিবেশ এর সাথে সম্পর্কিত একটা বিষয় আজকে আমরা রাখার চেষ্টা করেছি। আপনারা চাইলে আমাদের সাথে সরাসরি সংযুক্ত হতে পারেন এবং পাশাপাশি ফেসবুক এবং ইউটিউব কমেন্টের মাধ্যমে আপনারা আপনাদের প্রশ্ন আমাদের স্যারকে করতে পারেন। তো ধন্যবাদ সবাইকে। খায়রুল স্যার, আপনি যদি কিছু বলতেন।
ধন্যবাদ ডক্টর প্রীতম কুমার দাস। আজ 5ই জুন বিশ্ব পরিবেশ দিবস এবং পাবনা বিজ্ঞান ও প্রযুক্তি বিশ্ববিদ্যালয়ের 13তম প্রতিষ্ঠা বার্ষিকী। 2008 সালে পাবনা বিজ্ঞান ও প্রযুক্তি বিশ্ববিদ্যালয় যাত্রা শুরু করে। ইতিমধ্যে এই বিশ্ববিদ্যালয় তার কলেবর বৃদ্ধি সহ
স্যার মনে হয় আমাদের সংযোগ বিচ্ছিন্ন হয়েছে। তো আমরা আমাদের আরেকজন অতিথি শেখ রাসেল আল আহমেদ স্যারের কাছে যাব।
আচ্ছা, আজকে এই বিশ্ববিদ্যালয়ের দিবস 5ই জুন এবং পরিবেশ দিবস 5ই জুন উপলক্ষে আজকে সবাইকে শুভেচ্ছা জানাচ্ছি এবং প্রথমেই বিশেষভাবে কৃতজ্ঞতা প্রকাশ করছি আজকে আমাদেরকে এখানে ইনভাইট করবার জন্য ডক্টর প্রীতম কুমার দাস স্যারকে। আর উপস্থিত আছেন আমাদের অ্যাসোসিয়েট প্রফেসর স্যার ডক্টর মোহাম্মদ এন হুদা স্যার। তো আমি বেশি কথা বলবো না আসলে, কারণ আমরা সবচেয়ে গুরুত্বপূর্ণ যে মুহূর্তের জন্য অপেক্ষা করছি, স্যারের কথা, স্যারের প্রেজেন্টেশন এবং স্যারের যে এক্সপ্লানেশন, সেই জিনিসগুলো আমরা আজকে দেখব। তো তার আগে কিছু কথা বলবো যে পাবনা বিজ্ঞান ও প্রযুক্তি বিশ্ববিদ্যালয়কে বিশ্ব পরিমণ্ডলে আসলে মানে পরিচিত করবার জন্য আমাদের যে প্রীতম কুমার দাস স্যার যে কর্মকাণ্ড মানে পরিচালনা করছেন, এর জন্য আমি সত্যিই খুব ধন্যবাদ জানাতে চাই তাকে। কারণ এই ধরনের কাজ 184তম ওয়েবিনার, এটা খুব সহজ ছিল না আসলে। তো এটা খুব সহজ ছিল না, এবং এই ধরনের কাজ আন্তর্জাতিক পরিমণ্ডলে বিভিন্ন ধরনের এবং অসংখ্য রিনাউন্ড প্রফেসর এবং ইভেন নোবেল প্রাইজ যারা পেয়েছেন তাদেরকে তিনি আমাদের সঙ্গে পরিচয় করে দিয়েছেন, পাবনা বিজ্ঞান ও প্রযুক্তি বিশ্ববিদ্যালয়কে পরিচয় করে দিয়েছেন। এবং এটা সম্ভব হয়েছে আমাদের বর্তমান মাননীয় ভাইস চ্যান্সেলর স্যার উপস্থিত আছেন এখানে, তার
হ্যাঁ,
সহযোগিতা
অবশ্যই
না
স্যার।
পেলে এই জিনিসগুলো আসলে সম্ভব হতো না। তো আমি খুবই আগ্রহী, যেহেতু আমি বর্তমানে সোলার সেল নিয়ে একটু কাজ করছি, স্যারের কথা যখনই শুনেছি স্যার আজকে সোলার এনার্জি ম্যাটেরিয়ালের উপরে কথা বলবেন, এই জন্য আমি আসলে এই লোভটা সামলাতে পারিনি, অংশগ্রহণ করবার জন্য অনেক অপেক্ষা করেছি। তো যেহেতু আমাদের মাননীয় উপাচার্য স্যার উপস্থিত হয়েছেন, আমি আপাতত আমার কথা সমাপ্ত করছি। ধন্যবাদ প্রিতম কুমার স্যারকে।
ধন্যবাদ শেখ রাসেল আহমেদ স্যার। আমাদের মাঝে আমাদের মাননীয় উপাচার্য স্যার ডক্টর এম রোস্তম আলী স্যার ইতিমধ্যে সংযুক্ত হয়েছেন। স্যারকে আমরা অনলাইনের মাধ্যমে আমাদের অনুষ্ঠানে স্বাগতম জানাচ্ছি। স্যার, আপনাকে অনেক ধন্যবাদ এবং আমাদের ওয়েবিনারে স্বাগতম স্যার। তো আমরা আজকে আমাদের যে discovery of the efficient solar energy absorber material to mitigate global warming. আমি সত্যি দুঃখিত, আমি সংযোগ বিচ্ছিন্ন হয়ে গেছিলাম। আমাদের সাথে উপস্থিত আছে আমাদের মাননীয় উপাচার্য স্যার ডক্টর এম রোস্তম আলী স্যার। স্যারকে আমি আমাদের ওয়েবিনারে স্বাগতম জানাচ্ছেন। স্যারকে কিছু বলার জন্য অনুরোধ জানাচ্ছি।
ধন্যবাদ। আমি মনে করেছিলাম এটা জুমে হচ্ছে, কিন্তু জুমে না, এটা তারপরে ল্যাপটপে ওপেন করে দেখি যে না। তারপরে সবাইকে স্বাগত। আমাদের ইউনিভার্সিটিটা এটা বাংলাতে মনে হচ্ছে, এটা যে গেস্ট স্পিকার তিনিও বোধহয় বাঙালি।
জি, আমি বাংলাদেশী।
জি জি, ধন্যবাদ। আমি মনে করছিলাম ইংলিশে বলতে হবে, বাঙালি যখন আছে বাংলাই বলি তাহলে।
জি জি, অবশ্যই, বাংলা খুব ভালো।
ওয়ালাইকুম আসসালাম, আপনাকে স্বাগত।
জি, ধন্যবাদ।
আমি এই বিশ্ববিদ্যালয়ে প্রধান হিসেবে আপনাদেরকে স্বাগত জানাচ্ছি। যে ধ্যান ধারণা নিয়ে এটা শুরু করেছিল আসলে মুজিব বর্ষের, আমাদের মুজিব শতবর্ষর উপলক্ষে এটা শুরু। আপনাদেরকে এই বিশ্ববিদ্যালয় সাথে পরিচিত হওয়ার জন্য আমি আপনাদেরকে ধন্যবাদ জানাচ্ছি। আর এই ডক্টর প্রীতম কুমার দাস যে এই ধরনের একটা প্রোগ্রাম আয়োজন করেছে, মাঝে মাঝেই শুনি ওয়েবিনার করছে, তো আমি সংযুক্ত হওয়ার জন্য চেষ্টা করি, কিন্তু সময়ের অভাবে পারি না সংযুক্ত হতে। আপনারা বাংলাদেশের জন্য বিদেশে থাকেন, বাংলাদেশের মায়া আপনাদের থাকে সবসময়। আপনারা হাজার হলেও বিদেশে অবস্থান করলেও আপনারা নারী পোতা বাংলাদেশই আপনাদের দেশ। আসলে বাংলাদেশের যদি ডেভেলপ হয় আপনাদেরও ভালো লাগবে, বাংলাদেশের যদি উন্নত হয় তাহলে আপনারা বুক ফুলিয়ে বলতে পারবেন বিদেশিদের কাছে আমাদের দেশও উন্নত হচ্ছে। তাই তোমাদের দেশ উন্নতি করতে পারছে তার আমি যখন জাপানে যাই তখন দেখি রাস্তা, এখন আমিও বলতে পারি আমাদের দেশেও এরকম ফ্লাইওভার আছে, শুধু তোমাদের দেশে নাই, আমাদের দেশেও এখন ট্রেন যেটা দেনসা যেটা বলে জাপানিতে, ইলেকট্রিক লাইন, সেটা আমাদের দেশেও শুরু হয়ে গেছে। শুধু ওই দেশে যে হচ্ছে তা না, আমরাও চাই আমাদের দেশটা উন্নত হোক। এইভাবে আপনারা যদি এইভাবে দেশকে সহায়তা করেন তাহলে দেশ আরো এগিয়ে যাবে। দোয়া করেন আমাদের জন্য। আপনারা বিদেশে থাকেন, দেশে আমরা থাকি, যেভাবেই থাকি ভালোভাবেই থাকি, আপনারা দোয়া করবেন। আর এই ধরনের প্রোগ্রামে অংশগ্রহণ করার জন্য আপনাদেরকে আরো অশেষ ধন্যবাদ জানাচ্ছি। ধন্যবাদ সবাইকে আজকের এই ওয়েবিনারের জন্য। আমি একটু ব্যস্ত, তা আমি একটু পরেই অন্য অন্য কাজে ব্যস্ত হয়ে যাবো, কিন্তু ফাইল ওয়ার্ক সবসময় ফাইল ওয়ার্ক করতে হয়। ভিসি পদ বা অ্যাডমিনিস্ট্রেটিভ পদ মানে ফাইল ওয়ার্ক, কারণ কোনো কাজ নাই, বসে থেকে খালি ফাইলে সই কর, অনুমোদন দেব, এটাই আসলে আসলে মেইন কাজ। তো আপনাদেরকে অশেষ ধন্যবাদ, আপনারা ওয়েবিনার চালিয়ে যান, আমি যতক্ষণ পারি এখানে থাকবো। ধন্যবাদ সবাই।
ধন্যবাদ, আপনি কষ্ট করে আমাদের সাথে আছেন, এজন্য আপনাকেও ধন্যবাদ।
জি স্যার, আপনাকে অনেক ধন্যবাদ। আমি জি স্যার, অনেক অনেক কষ্ট করে সংযুক্ত হয়েছেন। আমি আমাদের আজকে 14 স্পিকারের কাছে যাব, তার আগে আমি স্পিকার সম্পর্কে একটু আপনাদেরকে জানিয়ে নিই। আমাদের স্যার সম্পর্কে বলছি যে ডক্টর মোহাম্মদ নুরুল হুদা স্যার is a tenured associate professor in the Department of Physics at the University of Texas at Arlington, এবং his research interests are in theoretical and computational condensed matter physics with an interest in strongly correlated F-electron system as well as application of the metal oxide to solar energy conversion process for renewable energy. Dr. Huda completed his bachelor and master's degree in physics at the University of Dhaka in Bangladesh, and his master's in applied mathematics was from the Department of Applied Mathematics and Theoretical Physics at Cambridge University, UK. Afterwards, he completed his PhD in physics from the University of Texas at Arlington. He was a postdoctoral fellow in physics at the University of Texas, Austin, and the research associate at the National Renewable Energy Laboratory, NREL. Dr. Huda has more than 90 papers published in referred journal and several others publications as book chapter and conference proceedings. So far, his ACE index is 28 according to Google Scholar. He has given 30 invited talks and colloquiums in the USA and abroad. Dr. Huda is a fellow of the Cambridge Commonwealth Trust and a member of the Sigma Xi Honor Society. He served in organizing committee of several national and international conferences and membership engagement committee in Materials Research Society. He was one of the founding coordinators for the Global Material Networks. আমরা স্যার এডুকেশন এবং অ্যাপয়েন্টমেন্ট দেখতে পাচ্ছি। স্যার তার ব্যাচেলার ডিগ্রি ঢাকা ইউনিভার্সিটি থেকে 1994 সালে এবং পিএইচডি সম্পন্ন করে 2004 সালে ইউনিভার্সিটি অফ টেক্সাস আর্লিংটন, এবং পোস্টডক শুরু করে 2005 সালে, এবং সে অ্যাসিস্ট্যান্ট প্রফেসর হিসেবে জয়েন করে ইউনিভার্সিটি অফ টেক্সাস আর্লিংটনে 2009 সালে, এবং সেই ধারাবাহিকতা এখন সে সেখানে অ্যাসোসিয়েট হিসেবে কর্মরত আছে। আমরা তার বিভিন্ন অ্যাওয়ার্ডস এবং অনার দেখতে পাচ্ছি। এটা স্যারের রিসার্চ ইন্টারেস্ট কন্ডেন্স ম্যাটার থিওরি, কম্পিটিশনাল ম্যাটেরিয়াল ফিজিক্স, strongly correlated F-electron system, materials, prediction of the first principle, foundation of quantum mechanics, teaching interest, quantum mechanics, statistical mechanics, advanced electromagnetic theory, and solid state theory. এটা স্যার গুগল স্কলার আইডিস, স্যারের সাইটেশনের মোর দেন 3286। এটা পাবলিকেশন লিস্ট, আমরা কিছু অংশ দেখালাম, আমরা দেখেছি স্যারের 80টার উপরে পাবলিকেশন। সবাইকে ধন্যবাদ। আমরা আমাদের আজকের যে মূল আকর্ষণ, আমরা এখন আমাদের শ্রদ্ধেয় স্পিকারের কাছে চলে যাব। স্যার, আপনাকে স্বাগতম, আপনি স্যার শুরু করতে পারেন।
ধন্যবাদ। মাই ফার্স্ট কোশ্চেন, আপনারা কি আমার স্লাইড দেখতে পাচ্ছেন?
স্লাইডটা একটু ব্ল্যাক, এখন দেখতে পাচ্ছি স্যার।
আচ্ছা, নাও ইজ ইট ইন দ্য প্রেজেন্টেশন মোড?
ইয়েস স্যার, ইয়েস।
দেখা যায়।
থ্যাংক ইউ। তাহলে আমি লেট মি গেট দ্য লেজার। ধন্যবাদ আমাকে ইনভাইট করার জন্য। প্রথমত পাবনা বিজ্ঞান এবং প্রযুক্তি বিশ্ববিদ্যালয়ের 13তম বর্ষপূর্তি উপলক্ষে আপনাদেরকে শুভেচ্ছা জানাই, এবং আমি নিজেকে খুব সৌভাগ্যবান মনে করছি যে এই দিনে আপনাদের সামনে প্রেজেন্টেশন দিতে পারছি বলে। অবশ্যই ডক্টর প্রীতম কুমার দাস, মেনি থ্যাঙ্কস টু ইউ আমাকে ইনভাইট করার জন্য, এই একটা ভালো উদ্যোগে আমাকে সংযুক্ত করার জন্য। I have seen the list of the speakers in YouTube pages. There are impressive presentations in there. I'm really feeling fortunate to be a part of it. And it's a very good initiative to connect students with the international speakers and audience. এবং ভিসি স্যার, আপনি আছেন এখানে, আপনাকে আবারও ধন্যবাদ জানাচ্ছি। আপনি একটু আগে বললেন যে দেশকে যদি আমরা বাইরে যারা থাকি সহযোগিতা করি। আমি একটা কথা বলি এই সময়, সেটা হচ্ছে যে দেশকে সাহায্য করা এটা আমার জন্য একটা একটা ইম্পসিবল জিনিস মনে হয়। মানে দেশকে আমি ঠিক সাহায্য করার ধৃষ্টতা রাখি না। আমি যেটা বলি, যদি দেশের সাথে আমি সংযুক্ত থাকতে পারি এবং কিছুটা হলেও যদি সার্ভিস দিতে পারি, সেটাই আমি খুব কৃতজ্ঞ থাকবো তাহলে। মানে বাইরে এসে যে অভিজ্ঞতা বা নলেজ বেস যেটা তৈরি করেছি আমরা, আমি এবং আমাদের সাথে আরো অনেকে আছেন এই ওয়েস্টার্ন ওয়ার্ল্ডে, আমরা মোটামুটি সবাই মনে করি যে দেশের সাথে সংযুক্ত হতে পারাটাই সৌভাগ্যের ব্যাপার, যতটা পারা যায়। আচ্ছা, after this preamble, now let's start the talk today. Because today is the Global Environment Day as declared by United Nations. So the theme of today's presentation will be on mitigating global warming. That means to preserve the environment, the nature. Today, this year's theme for this Global Environment Day is to renovate the relation between human and the nature. The way we kind of harm the nature, it's now time to repair some of the harm if we can. In some prediction, by some prediction, it may be little late, but at least we should start somewhere. Now, the title of my talk today, as you can see, is based on solar energy. Solar energy, why solar energy, and how it's related to mitigating the global warming. It will come in my presentation, and also my personal research, my group research, what we do in this particular theme. The first slide is basically a view of my campus, the University of Texas at Arlington. This view is from the a northeast corner. We have in this campus about 50,000 students. That's a pretty large campus. And it's one of the 13 campuses in University of Texas. Now, to start to define the problem of global warming or the crisis we create, sometimes we think that the impact of global warming is coming in future. That means it may be our children or our grandchildren's will be the sufferer of the harm that we are doing right now. As you can see, this news article that was published last week, May 31st, the article says that more than a third of heat death are tied to climate change. So we are already suffering from the climate change global warming problem as of now. This news was based on a paper recently published in Nature Climate Change. Among many things, the paper published this particular plot, which shows the temperature change, the annual average temperature change on this planet, on Earth, from 1900 to 2021. So it's a very recent result. And as you can see, over the time, the temperature was pretty much flat. And then suddenly, from around 1980s and on, the temperature is start increasing. And at this time, the average temperature has increased by almost 1 degree. If I think like this is 21.5, now it's almost reaching to 23. It's more than 1 degree increment. Now, it seems small, 1 degree Celsius increase. However, the impact of this 1 degree Celsius change is enormous. For example, this slide shows some of the impact that happens recently in the last 4 or 5 years. Frequent flooding in many places in all over the world. Increasing frequencies of tornado, hurricane, and cyclones. And progressively, their size is getting bigger and bigger. One thing we all know is the ice cap melting in the North Pole, especially, and that is increasing the sea level. And one of the older article in New York Times, it mentioned like 5-6 years ago, that because of the sea level rise by few inches, a major part in the south coast of Bangladesh can be underwater. Another impact that we have seen, especially last year, several large-scale wildfire. I'm sure you have seen in the news, some part of Australia were burning for several months. Western coast of USA in the California region, almost 6 months long wildfire was burning in different places. These are not like regular wildfire that that happens due to seasonal change. These are extremely large scale wildfire. And then, of course, the drought. So these are some of the major things that has been happening in the last 4 or 5 years. And another impact that is not shown in here is that severe winter weather. The winter weather in Texas, where I live, is usually very mild. It's almost like similar winter weather that we get in Bangladesh. This year, we had almost a week of snow and temperature below freezing. This is unusual for Texas. These all changes that we are seeing now is basically due to the global warming, and probably this just 1 degree Celsius change of average temperature compared to the last century. Now, why this temperature is increasing? It's mainly because our increasing appetite of energy consumption. For many reasons, we are continuously increasing our energy intake, and most of those energies are coming either from oil, that gasoline that we get from mining, then natural gas, burning natural gas, and coal. So if we consider these three contributions, now this is up to 2050, these are projection, and this projection has some optimism that the green region is coming or it will be increasing. These are the renewable sources. But as of now, 2020, I think I have an indicator here. As of now, in here, as you can see, this whole thing is basically burning fossil fuel and emitting carbon in the atmosphere. And if we convert this number that is given in million tons of oil equivalent, if we convert into gasoline, the way we usually talk, it's like 1,200 crores tons of gasoline, like 1200 koti tons of petroleum that we use. If we just consider this thing, this is a humongous number that we have been using right now around the world just to power ourselves, to drive car, for the electricity, running industries, everything inclusive, building high-story building. These are the energy consumption, and it will keep increasing. Now, what the problem is, as we mentioned, that it is emitting carbon in the atmosphere. How much carbon? So this is another plot. This is not exactly up-to-date plot. This is up to 2005 or 6. And the numbers on this side is in billion metric ton of carbon per year. As of now means as of this plot, which is updated around 2005 and 6, we have been releasing 10 billion metric ton of carbon in the year. And these are different contributions from where they're coming. The petroleum, coal, natural gas, cement production, or this gas flaring that happens in the mine. These numbers, this is a big number, like billion metric tons. I just tried to make some easy conversion to see or to make a sense out of it. 1 metric ton of carbon under ambient pressure can fill this cubic box of 27 feet. This is an average height of a human. You can see that how big is the box looks like. Check this thing to 1 billion. This 1 billion now for 2005, this should be 10 billion boxes of this size of carbon dioxide. And if we really think like that, what would be the weight of those things? It is approximately 10 lakh crores kilogram of carbon. Like 10 lakh koti kilogram of carbon we are releasing in the year. In another way of seeing it, if we think about equal of a small Toyota car, then we are talking about 1,000 crore of car. Like if we keep increasing cars, so this is that I'm not talking the emission from the car. It is just the weight of the car. So this many 1,000 koti, 1,000 koti gari, Toyota gari jodi amra weight kori, ojon kori, almost that amount of carbon we are releasing every year in the atmosphere. This is a huge problem. We need to do something to mitigate this thing. Now, another study that was published in 2009 in Nature, which shows that even though this increasing trend of the average temperature that can happen and that is happening, this is a projection up to 2100, and if the trend goes on the same way as we're doing right now, then the temperature increase could be up to 7 to 8 degrees, as you can see. This is the median value at the middle. Now, this can be carved. This can be carved as this green, sorry, the blue region. Similarly, the carbon dioxide emission, this is shown in per particle per million part. It is increasing again, of course, but there should be something. There should be some mechanism to carve it, and this kind of carving of carbon dioxide emission is possible. Now, how do we implement this strategy? One of the way that we can definitely implement this strategy is by using renewable energy. There are several sources for renewable energy. It could be solar, biomass, hydroelectric, that is the electricity produced by waterfall, geothermal, by using the thermal heat from the earth, the wind energy, or the ocean energy. Ocean energy is basically utilizing the energy of the oceanic waves. For my personal interest, I am interested in solar energy. Why solar energy? This is an interesting fact that the amount of solar energy strike on Earth's surface every hour, if we take that energy and can utilize it, that is enough to power the entire Earth for a whole year. So 1 hour sunlight that can shine on Earth, if we utilize it, we can power the planet for a whole year. It is a very promising fact, and it is a scientific fact. It has been thoroughly calculated and shown. Now, what is the main challenge then? The main challenge is to find something that can absorb this solar light efficiently and then use that solar light to do something else, to produce electricity, to produce other fuels, reserve that energy in chemical energy like in battery or in hydrogen. But the main point the main challenge is to get a suitable, efficient material to absorb this solar light. My work is mainly for this presentation based on this fact, to get a suitable materials for solar energy conversion. So this is my motivation of research in my research group, the mitigation of global warming. We want to reduce, or we want to eliminate the disastrous fact that may happen within next 100 years. There are several mechanisms that are well known to convert solar energy into some usable form. One is photovoltaic. The PV materials in a basic form basically needs a PN junction, a diode kind of formation, and most of the photovoltaic cell that is available even now are made of silicon. So that photovoltaic cell, we know that it absorbs light, convert it into electricity, and then we can use the electricity to do something else. One of the things that is nowadays is popular is to drive a electrolysis cell by this photovoltaic cell. This is called PV electrolysis. What is done in here is that in this electrolysis cell, water molecule is split to make hydrogen. And then hydrogen is then stored to use it as a fuel to do anything that a regular gasoline can do. Now, these particular arrangements nowadays are very popular in the sense that there are several industrial applications even that is happening right now to produce hydrogen by this PV and electrolysis cell combination. Another way of doing the same work but combining these two into one single cell, that is called photoelectrochemical cell. In this cell, sunlight can be absorbed by a material, typically a semiconductor materials, and then this will produce the current within the material. We call it photocurrent, and due to the current, electrons will drive the reaction on the anode side. Oxygen will produce, and on the counter electrode side, hydrogen will be produced, and then hydrogen can be stored from here as well. Now, this is on a single cell, not like PV run a electrolysis cell. This is a very ambitious project. The proof of concept was shown in 1971. Since then, there are lots of fundamental and applied work was done, published, but this particular technology or concept is not yet at the industrial level versus this concept to produce hydrogen. PV, we all know, it is now ubiquitous everywhere. So these are the few places where we can directly use sunlight to either make electricity or make hydrogen in this device or by photoelectrochemical device. So the basic thing, the first step is to absorb the sunlight. Sunlight needs to be absorbed properly. To absorb sunlight, now let's see the solar spectrum. Now this solar spectrum, the outer line, the black line, is the spectrum that is outside the Earth's atmosphere. And when we get it on the surface of the Earth, some of the light is absorbed by the Earth's atmosphere. And then this plot, that the color plot inside the region, inside the yellow region, is what we get on the sea level, for example. The important message from this plot is that if we see here, the major part of the sunlight or solar energy that comes on the surface of Earth is on the visible range of the light, from red to the violet. So this is the maximum light we get from the sun on the surface of the Earth. So if we want to absorb light, we need some materials which can absorb all these range from the red to the violet. That means if we can absorb light somewhere around here, then all this thing will be absorbed. From red to the right, these are infrared region. So if we have a material with a band gap around 1.1 or 1 electron volt, then we can get all these lights from the infrared to up to everything. So we need a materials, at least a material which has a proper band gap. And that is the first criteria. We need to get a material that will have a proper band gap to absorb the light, and definitely those kind of material will be a semiconductor materials. Now let's get a closer picture of material, how the material look like. This is shown material at different length scale. On the right side, these are the smallest scale, the fundamental particle state, where we can see if we get a nucleus, then proton and neutron can be made up with quark, and each of the individual quark are even at a smaller scale. And of course, electron by themselves are also at very, very smaller level. To probe this area, to understand the physics of this area, because they are at extremely small scale, we need high energy. Hence, this goes to the high energy physics. For our work, we are not doing work on the high energy physics. Mostly, we are interested in this range of scale. So materials, then the molecular unit of the materials, the atoms of the molecules, and the nucleus in the molecules. We need to know some of the nuclear property to get a proper understanding of the atom, to the molecule, and to the material at a bulk scale or a crystalline scale. So if we think about condensed matter, nanoscience, and chemistry, they basically work on this length scale from the bulk to the 10 nanometer scale, and the nuclear physics and atomic physics goes in this region. And nuclear physics definitely work with the nucleus, atomic physics goes with atoms and the nucleus, where electron goes around the nucleus. So if this is the picture that we know about materials are made of atoms are made of electron and nucleus, then the question is, then how do we understand the light absorption in this system? To understand this thing in a quick review, we will start with atoms. So we'll take an atom, look at the atomic picture, and we'll try to explain how light is absorbed. A brief history of atom. I don't want to go a detailed historical description, but in a very short statement, the concept that every material has a unique building block, the smallest building block, this concept was developed approximately 2,400 years ago by some Greek philosopher, Democritus. And then this box shows the timeline of recent understanding of atom and their experimental realization. This kind of picture that we sometimes see, that a nucleus and electron goes around it in all different directions. This is a cartoonic picture of atoms. We draw it to show a simplified figure. A electron microscope photograph of an atom for an hydrogen atom will look like this. This is taken from Physical Review Letters published in 2013. And this spherical cloud clearly shows the s electron properties of the atoms. Now let's understand, if we get the fact of light absorption, so we get an atom where electrons are moving around the nucleus. This is basically the Rutherford model. And at the end of 19th century, people found that atom can have spectral properties. That means a different atom for different elements can emit light in different colors. Every atom has their characteristics spectra. And this kind of a spectra was assigned to each one of the atom according to their properties. So we knew this experimental fact. We had a somewhat understanding that electrons will go around nucleus. And then from these two pictures, it was not possible to describe why this kind of color spectra is shown or is found from an atom. Explanation was building up around 1900. People know at the time, which was called photoelectric effect. What photoelectric effect is, if light shines on a metal surface, electron can be emitted, electron can be ejected from the surface. Now, the velocity or the kinetic energies of the electrons depends only on the color of the light, not the intensity of the light. It was thought that if there are high intense light, because you are now shining more and more energies, electrons should have higher velocity, higher kinetic energies. But it was not the case. Only when the color is changed, then only this velocity or the kinetic energies of the electrons were changing. This fact was explained by Einstein with the help of idea that was developed by Max Planck. Idea was that light is not a continuous electromagnetic wave. It is rather a quantized energy packets. Each of the packets are called phonon. And phonon have energies that is related to the wavelength or the frequency of that color. So red color will have low energy, violet color will have higher energy. Depending on the color of the photon, the energy of a wave packet will change, and the electron kinetic energy will be equal to the energy of the incident photon. This explanation confirmed Max Planck quantization of light idea. So this was in a way a beginning of early quantum mechanics. Because of this contribution, Einstein get Nobel Prize, I think after 1925. So Einstein got Nobel Prize not because of relativity theory, but explanation for this photoelectric effect. Now, once this explanation was established, he published that paper in 1905, same year when he published his paper on special theory of relativity. When this concept was published and well known, Then in 1912, 1913, Niels Bohr, he proposed this model of atom. So this model of atom incorporate the photon package, quantized package, and this spectral definition or the spectral emission from atom. In fact, the model Bohr proposed was motivated to explain this phenomenon. What it does is that when a photon is shined on an atom, for example, then an electron can absorb this energy and can get excited to a higher energy level. Once it is at the higher energy level, then it can de-excite to a lower energy level. When it de-excites at a lower energy level, then the energy difference between higher state and the low energy state, this energy difference will be exactly equal to the energy of the emitted photon. And if this emitted photon energy is equal to one of those colors, if it is like green color, then we will see green light from this atom. So this atom, which is, or this model of the atom, which almost mimic the solar system orbital, was established. It is like a pre-quantum mechanical description of atom, which explains these spectral properties, and also it helps us in a way to understand that how light is absorbed. Light is absorbed, or a photon is absorbed, and then electron get excited from an occupied lower energy level to an occupied higher energy level. This is the basic mechanism of light absorption in atoms, in molecules, or even in solid. Now, we just talked about one atom. So what happens when you bring together many atoms? So I just try to give an example of sodium atom. The reason I picked up sodium, because sodium has one valence electron, that is S electron. It is mostly a spherically symmetric orbital. If we bring two sodium atoms, then those orbital overlap. They create an energy level or energy envelope around that sodium dimer. Now, if we bring more sodium atom, it's a hypothetical system, then all those energy levels start overlapping and create a continuous energy level around those atoms aggregate. Now, we can extend this atom to the left and to the right up to infinity, or make a crystal out of this in 2D or 3D. Then these energy levels will form a continuous band. We call them band when you talk about a large system, solid system. A real picture of band, how really bands look like in a solid, I presented an example, for example, for silicon. When we have silicon, then these lines, as we see, are these bands that in this cartoon picture, as we show that they keep overlapping and then make a continuous energy levels. These are those continuous energy levels for silicon. By convention, this is 0 electron volt. Anything below 0 electron volt, these are all occupied orbital. That means these are occupied by electrons. Anything above 0 electron volt, these are unoccupied orbital. And the minimum gap between occupied and unoccupied orbitals, we call them band gap. And this kind of picture in solid state is called band structure for a solid. We will see it in more cartoonistic form in here, because this band gap is important. It is occupied to unoccupied level. And we just saw for an atom that when electron get excited, we get light absorption or light emission when it de-excite. So we need to define this thing very clearly. So this is the band gap from the top of the valence band to the bottom of the conduction band. The smallest energy difference will be the band gap. For a real system, another system, for example, this is iron oxide, Fe2O3. This is the band structure for iron oxide. Iron oxide is a very common material. The rust we see on iron metal is basically iron oxide, Fe2O3. And its band structure looks like this. Again, this is 0 electron volt. Anything below 0 electron volt, these are occupied bands or occupied energy levels. Anything above 0, these are unoccupied or empty energy levels. And then we call this the valence band. This is the conduction band. And this would be the band gap, the minimum difference of energies from occupied to unoccupied level. The highest point is called valence band maximum. Lowest point of the unoccupied band is called the conduction band maximum. So these are the conduction band, these are the valence band. When electron get excited to the conduction band, electron can technically be taken out from there. That means electron will conduct through this empty band to somewhere else, wherever you want to take that electron to constitute a current. Just another terminology, the top of the valence band, the highest occupied band, usually called the Fermi energy. Now, so far we have seen band structure, the energy levels for crystalline solids, the band gap. Now, for our purpose of research, we do theoretical and computational condensed matter. So we calculate everything. So now for a material, once we want to work on a materials, we then calculate the band structures. We identify the band gap and its nature. Nature means the band gap could be a direct gap or an indirect gap. From the band structure, we get this information. And then thirdly, we calculate the light absorptions, meaning when electron get excited from the valence band to the conduction band, the electron absorbs the light absorption and electron get excited. What is the probability? Sometimes at the minimum gap, electron cannot get excited because of some forbidden rules. So we calculate all these things. Most of the time, we have found that for a particular work, the material we get from nature as it is may not be the most efficient material. We need to change something. We need to tune the electronic properties of the materials to get the right light absorption and the conduction properties. For example, silicons, even though silicon is commercially one of the most popular photovoltaic materials, but I think most of you know that the efficiency of silicon, the commercial silicon, is no greater than 15%. That means whatever light it absorbs, around 15 or slightly more can be utilized to make current. Rest of the energies are wasted. The best performing silicon single crystal efficiency goes up to 25% or less than around 25%, but that is a single crystalline silicon, meaning to make that single crystalline silicon is a very expensive endeavor. So just a silicon, we cannot go far above some certain efficiency range. Hence, we need to find, let's say, new materials. We did, like in industry or in current affairs in photovoltaic. There are other materials, but they come because we want to go beyond the limitations of silicon-based photovoltaic. To do this thing, to do all these things from a theoretical perspective, we need to now define a theoretical methodology. I will be very quick in describing some of the methodology. Most of them will be in qualitative form. I am not intending to show or explain equations for this presentation, even though the computations or theoretical calculations are based on theoretical model. Now, we are talking about electronic properties. That means the electron, how they move in those energy levels. Hence, this should be done by some quantum mechanical approach. The second thing is that we are talking not about one electron or two electrons, it's many, many electrons. If we consider a solid, 1 mole of solid will have 10 to the power 23 atoms. If it is sodium, for example, then one valence electron, that will make 10 to the power 23 electrons. It's a huge many-body problem, and solving many-body problem is an outstanding challenge for physics till to date. We all know we can solve exactly for one particle system, two particle system. Even if three particle system, there has to be some approximation or numerical solution. Analytical solution is getting more challenging. From 3 and above, it's almost impossible to get an analytical solution. So there are methods, quantum mechanical methods, to handle this challenge. One method that is very popular is the wave function based method, which was initiated by Hartree and Fock. around 1920s or mid-20s. This is a wave function based method. That means if there are n number of particles, there will be 3n degrees of freedom. So this is, even though this is a much simplified method compared to the hardcore Schrodinger equation in quantum mechanics, but still, if the number of electrons are higher than 3n degrees of freedom, if we want to make the computations or calculations slightly more realistic, this can be prohibitively impossible for a real-life crystalline computation. The method, another method, is called density functional theory. This was proposed in 1964. Then it got implemented in computational form so that material can be calculated is around mid-80s, 1980s. This method, if we compare to the wave function based method, it's just depend on the electron density, rather ground-based electron density, and the electron density will be a function of position. Hence, it will have only 3 degrees of freedom. Both the method are used in physics and in chemistry and in material science to calculate material properties. My work, especially, we do work on both of the branch, but for today's presentation, the results that I will show is based on density functional theory. In short, density functional theory, this is a first principle method. First principle method means for computation or calculations of a material properties, all we need is the crystal structure of the material and the atomic position within the crystal. If we have that information, then we can calculate everything from there, all the properties of that materials simply from the atomic information of the crystal for that material. No other experimental information is needed to do the computation or calculations. That's we imply this first principle method. The theorem for density functional theory was proposed by Hohenberg and Kohn in 1964. This is the paper where they published the first theorem, where basically they prove this statement that if we want to calculate all the ground state properties for a material, all we need, the density and the properties will be functional of density. I would like to, for the students, mention or would like to draw your attention to this word. This is not function, this is functional, and the mathematical notation changes. Density is a function of R, but this F, some functional of density, which is represented by the square bracket. A functional is basically a function of a function. So this F is a function of density, and density itself is a function of R. So this functional dependence is the main entity of this Hohenberg-Kohn theorem. For this theorem and the implementation of the computational algorithm, Walter Kohn, he received Nobel Prize in 1998. So density functional theory is a first principle and is basically the state-of-the-art method for electronic structure calculations. It is now used everywhere for all kind of material calculations because it's reliable and relatively faster. All we need for density functional theory computations is the ground state electron density. Density functional theory, it has been shown over the years that it is an exact mathematical theory. So there is no approximation within the main theory. However, for computational implementations, some approximation is made. For one of the reason is that the universal functional form of the electron density, the exact form is not known, and that was not defined in the original papers by Walter Kohn and his collaborators. Now, to do this computation with this density functional theory for all the material properties, these are large-scale computations. For the large-scale computations, we do need very high computing system. We are fortunate in Texas because we have what we call, for our University of Texas, we have at Texas has Advanced Computing Center. And this Texas Advanced Computing Center is very well equipped with several supercomputing resources. And this was ranked one of the top 10 supercomputers in the world a year ago, just last year. Of course, it changes in every year, but still I checked 4 days ago, it is still within the top 10. A year ago, it was the #1 in supercomputer in the world. So we use these supercomputing facilities to compute the properties of materials that we want to understand and know using density functional theory. Now, what do we actually need to know? What to do? Once we get a material, how do we improve the light absorptions? What should we calculate? So there are several things, a simplified description. First, we need to probably tune the gap. Why tune the gap? The band gap is the primary quantity which will define the energy of light absorption. So if the band gap is not at a right value, we need to change the gap for a material. For example, we showed an example of iron oxide, Fe2O3, that has a gap of 2.2 electron volt. If we want to absorb light efficiently and more light absorption under sunshine, the gap should start from at least 1.5 electron volt. That means we need to reduce the gap from 2.2 to 1.5 electron volt. How do we tune that gap? This is first thing we do. Secondly, and make sure that when you reduce the gap, at that reduced gap, electron excitation can happen. It is possible. It is allowed. Because there are certain cases when this transition is forbidden. For example, if the occupied and unoccupied band at the band gap both are like s orbital to s orbital transition, or p to p orbital transition, or d to d orbital transition, those are forbidden, prohibited. S to p, p to d, those are more favorable. So we need to not only change the band gap, reduce the band gap, but also we need to make sure that the band properties is good enough so that favorable transition happens, S to P, P to D, those kind of transition. Then also we need to make sure that electron mobility in the material is good. That means the electron conduction is good. Why this is necessary? Because once electron is excited, unless the electron moves away from the side, that means it is conducted through the materials, electron will de-excited back to the valence band. And that usually happens within a picosecond, not even, so that's a very tiny, small time. Electron has to be moved out from there to prevent that electron de-excitation. That requires good mobility. And then in some of the materials, some of the softer materials, we have found that because solar light comes into the materials and electron absorb the energy, and then it gets excited to the upper band, the energy that requires to make that excitation, sometimes that energy is good enough to dislodge an atom within the material, and then the atom starts diffusing through the material. That usually degrade the material property. We don't want that to happen. So we need to make sure or select a material or tune the material in such a way that material degradation upon solar energy irradiation doesn't happen. And then, of course, for practical purpose, we need to have a materials which is easily available on Earth. Those are not rare materials like platinum or indium. Those are very expensive materials. So it doesn't, we design a material or take a material for solar applications which are abundant in Earth. And thirdly, and lastly, not exactly the last, meaning at least one of the last point in this list is that a large scale synthesis is possible for this material system. If we just do a lab scale synthesis and it is good for that, then it cannot be deployed in large scale. So the last 2 points are more practical points. Usually when we work on this point to do the calculations, we pay attention to the last 2 points as well, so that if this is successful, somebody can take our idea and then synthesize the material in the lab. All these calculations we do in a software environment, a package which is called VASP. It calculates all these electronic properties, or we use this package to do the calculations. Now, how to do this? How to tune the gap? There are several methodologies. One could be by doping. For example, if we have a material gallium nitride, if you see green lasers, that most likely from gallium nitride. The gallium nitride has a very large band gap, more than 3 electron volt. To reduce the gap, we can dope aluminum, for example, in gallium nitride, and that will reduce the gap. So a doping could be a possibility for any materials. Gallium nitride is shown here as an example. Another process could be passive co-doping. Passive co-doping means we dope zinc on the gallium side. As zinc and gallium has different oxidation state or charge level, this will create a charged impurity. To compensate the charge impurity, a nitrogen can be doped at an oxygen site. So this zinc nitride co-doping is called passive co-doping because that neutralizes the charged impurity. So these are both of these methods can reduce the gap. However, doping sometimes because of unintentional doping problem, this can create a poor crystalline material. And another methodology that is used as well is by predicting novel alloys. Like if we start from gallium nitride, it's not just doping, getting a new alloy, completely new alloy. Alloy means it may have new crystal structure, different kind of stoichiometry. To predict crystal structure at an arbitrary stoichiometric material is extremely challenging. And another method that also used you can find in literature is by reducing the dimension, like getting a gallium nitride nanowire or gallium nitride nanocrystal. So making those reduced dimensional structures can also change or tune the band gap properties. For this presentation, I will show example for the first 3. We will not show our work on this, the 4th point. So how this doping change the band gap? Now, most of my work or my group's work are on metal oxides. So I will take this as a prototype and show some cartoon to give you an idea how band gap actually change. Let's say that this is a metal oxide band, valence band and the conduction band. If we dope nitrogen, as I just shown on the last slide, at oxygen place, what it does that it places those impurity nitrogen p band above the original valence band. Because of the placing of this nitrogen p band above the valence band, the effective band gap is now smaller than the previous one. The previous one was from the green to green. Now we have a gap from the orange to the green. It's somewhat smaller. Now, of course, now we can dope on the metal side for the metal oxide. If we do that, so doping at the metal side, the metal D band, if we consider transition metal, those D band usually sits below the valence band, somewhere within the valence band, basically. And then once the metal D band sets in there, there is a hybridization with the oxygen P and the metal D, the impurity metal D. This hybridization will basically push the valence band up. This is the hybridization is splitting, bonding, anti-bonding is splitting. Because of this splitting, the band gap can also get reduced. These are the 2 simplest mechanisms that I can show how we say that we tune the gap, we reduce the gap by doping. Now we will show some examples from our work. There are several publications on this tungsten oxide work. Some of the latest ones are not listed here. A tungsten oxide looks like this, a crystal. This is a unit cell for tungsten oxide. These blue atoms are tungsten, the red atoms are oxygen. This looks like a distorted perovskite structure where the A metal atom at the center is missing, where the laser point right now. This tungsten oxide, if we calculate the band structure, this is how the band structure looks like for tungsten oxide. Again, anything below 0 are occupied. This is the valence band, this is the conduction band. So when electron is excited, it should excite from the top of the valence band to the conduction band. Now, as you can see, the gap according to the band structure should be around 1.3 or 1.4 electron volt. Now, then we calculated the absorption coefficient. This basically shows the absorption probability. This is, again, I just wanted to make sure that we understand the color scheme. We wanted to absorb light as red as possible. So if we absorb light, let's say from 1.6 electron volt, or the gap is around 1.6 electron volt, then everything should be absorbed. Now, for this material, seems like from the band structure a promising one, because gap is started from 1.4 or something. It should start from below the red. So from the near infrared to everything should be absorbed. Now, when we calculated the optical absorption plot, what we have found, the absorption around 2 electron volt is not much. It's almost close to 0. 2 electron volt is around this color, is not even on the red side, on the yellowish orange color. That means at the lowest gap, where we started from 1.4, this thing is not absorbing. So this is, as I mentioned, that even there could be some, the gap could be small, but that at the smallest gap, light absorption can be prohibited or forbidden because of some dipole selection rules. Those came from crystal symmetry. So we can see here one of the examples that light is not being absorbed, even though there are energy bands. Light is not being absorbed around 1.4. It is started absorbing significantly after 2 electron volt. So once we understand the properties for tungsten oxide, now the goal is to increase absorption around this area so that it can absorb at least from the red light. Let's first talk about doping. Now here we dope nitrogen into tungsten oxide. So we mentioned that if we dope nitrogen on the oxygen side, nitrogen P level should sit on top of the valence band, hence the gap will be reduced. Why H is with nitrogen? The reason we put hydrogen, because nitrogen on the oxygen side will create a charged impurity level. Usually it's not good to have a charged impurity level. It acts like a electron trap. Electron cannot conduct. Hence, and hydrogen will passivate that charge. So co-doping is for that particular technical reason. Once we do that, we recalculated the absorption coefficient. Now, if I compare with the tungsten oxide, now if we see here, this is the tungsten oxide around 2 electron volt. Just if we pay attention, compared to 2 electron volt with nitrogen doping, it increased somehow. Now that increment is not significant enough. It did increase, especially the green line, which is light polarization along the Z direction. That has somewhat more improvement for light absorption. However, the overall improvement is not significant. So what to do? First of all, the light absorption is not significant enough. Secondly, because there is nitrogen-hydrogen doping, and in a real-life experimental scenario, it could be more nitrogen than hydrogen, and then there will be some charged impurity state within the band gap, and that can act as electron trap center. Not only that, usually those kind of trap centers create strain in the crystal. Hence, the crystalline sample in experiment will have poor crystallinity. Poor crystallinity, in other words, also contribute to high resistivity in the materials. Hence, doping, even though it shows some promise, but may not be a significant improvement to carry it further from here. So what we did after this is to go for the alloy. So what to do for alloy? Now, in doping, if we consider like silicon, it's a very well-known fact for the last 70 years that silicon can be doped N-type and P-type, and those kind of doping are usually 1 part in few million atoms. Like the doping concentration is very, very small. In general, for doping, crystal structure does not change. However, if the doping concentration for some reason is higher, and the doping is responsible for creating charge impurity, then as I mentioned in the last slide, crystallinity usually is not good. On the other hand, in alloying means that we are now putting significant number of foreign atoms into the crystal, into the host system, and hence the crystal structure can change and a new structure emerge, and also the stoichiometry of the compound, or the chemical formula of the compound can also change. So there are two new things coming on if we want to alloy the system or make a new alloy. New crystal structure, so we have to predict the crystal structure and also predict the stoichiometry. Now we mentioned that density functional theory is a first principle method in the sense that if we know the crystal structure and the atomic position, then we use the density functional theory to calculate everything. Now, if we don't know the crystal structure, rather we have to predict the crystal structure, that become an extremely challenging project. In fact, in 2004 or 5, there was an editorial published in the journal Nature. It mentioned at the time that it is one of the unsolved problem in solid state physics, that is predicting crystal structure entirely from theoretical consideration. Even though it's like more than 15 years passed by from 2004, the situation hasn't changed much in terms of crystal structure predictions. However, because of time, now we know more. We know more to approach the problem. This is also we have done in my group. So now we want to change the band structure or tune the band structure for tungsten oxide, not by doping, but by alloying. The first question then, what to alloy to have the desired effect? That needs a lot of reading papers, crystallography information, and testing. Of course, for our case, it's theoretical computational testing. So the target of this alloying is to get a new alloy to enhance the optical properties. That means tuning the electronic structure. The goal is to reduce the band gap for tungsten oxide. You saw that optical gap is really high. We want to reduce that and also raise the conduction band minimum. That means the conduction band minimum, wherever it was, we want to lift it somewhat more. One of the reasons for this conduction band uplifting is because when we use it for those photoelectrolysis process or electrochemical process, those need a higher conduction band above a value for hydrogen reduction potential. For PV, the second point is not so important. So, but because we are now targeting both of the technology or methodology, hence we want to reduce the gap and also try to raise or uplift the conduction band a little bit. And of course, we want to make sure that optical absorption is good around the fundamental smallest gap. What do we look for? We look for atoms which we will be alloying with tungsten oxide. Those atoms should be compatible with the desired orbital positions, so it does these things. So the first alloy that we published on this consideration was bismuth and copper in tungsten oxide. Now, the question why we choose bismuth in the first place. The reason is that we found that in this compound, which is well published and included in crystalline database, in like one of the biggest crystalline database is ICDS, a European database. In USA, there is American Mineralogist Society database, and also from published paper, we have found that bismuth, when it goes into tungsten oxide, it uplifts the valence band. So it raised the valence band because of oxygen 2p and bismuth 6s hybridization or coupling. Bismuth 6s sometimes are called lone pair electrons, but these are stoichiometrically active. Hence, this phenomena happens. So if the valence band rises from tungsten oxide, meaning the gap is now reducing. Why copper? Because again, we found another materials, which is copper tungsten, and we have seen that copper hybridizes with oxygen 2p for this oxygen, and then it can uplift the conduction band. So what we decided is that if we use bismuth, it works on the valence band. If we use copper, it works on the conduction band, and both of these actually work via oxygen 2p orbital. So instead of doping copper and bismuth in tungsten oxide, we will search for an alloy. Now, we'll search for a crystal structure for a new alloy, because there is no, when we started doing the work like 6-7 years ago for this particular alloy prediction, there was no publication on a system which has bismuth and copper together with tungsten oxide in new materials. Hence, first we need to search for a crystal structure, or we have to predict a crystal structure. This was one of the longest project we have. One of my PhD student, he worked on this project, and just to come up with these 2 points, it took almost 6-7 months to get the right thing into tungsten oxide. And then to predict the crystal structure, we developed an algorithm. And of course, we have to come up with this stoichiometry. This stoichiometry also comes from this algorithm. We started from existing structures from different database, and then we branch out to different category, define different type of stoichiometry, and finally come in this side. And another route was, there was a material project, that was funded by Department of Energy in United States. That material project can generate some structures. We took those as input as well to get some motif structures for this copper, bismuth, tungsten, oxygen alloy. In this stage, this motif structures stage, we have approximately 250 to 260 structures. We tested them all by our computation, and then finally we decided upon this stoichiometry and this structure and this crystal. And the crystal structure that we found, this is more details on the minerals that we considered. I skipped that one. The crystal structures that we found is this one. So this is the crystal structure that we predicted from our theoretical consideration for copper, bismuth, tungsten oxide. These bigger atoms, this magenta color, or probably, I don't know the name, these are the bismuth atom, the blues are the copper atom, the gray are the tungsten atom, and the red are the oxygen atom. This is a kind of a mineral which is grouped as scheelite structure, rather distorted scheelite structure. This is what we decided upon, that should be a ground state energy crystal structure for copper, bismuth, tungsten oxide. Now, once we decided on the structure, then we calculated the band structure. Now, this is the band structure. This is the valence band. Again, these are the conduction band, unoccupied band, and the gap occurs in here. Now, compared to tungsten oxide, this gap is smaller. But then the question is, what about the optical absorption? Because that is what we are targeting from the beginning. Now, this is the optical absorption we calculated. Now we can see that here at least the optical absorption is started at energy lower than 2 electron volt. In the next slide, we will compare again tungsten oxide and the new alloy. If we focus on here, as you can see, this is tungsten oxide, where the absorption, the light absorption around 2 eV was almost 0. This is our new alloy, where light absorption at 2 eV has improved significantly in this case. So the thing, or the goal of our work, go from tungsten oxide to a new alloy, was kind of successful, because we now significantly absorb light at a lower energy. It is started from around 1.6 electron volt, that what we calculated, and if we start from 1.6, we're basically absorbing everything. Because if you go from 2 to 6 electron volt, this covers the whole range of the visible spectra up to some ultraviolet region. And as you can see, that the light absorption probability increases as you go to the higher energy. Now, these are all theoretical work that we have done in our group. And then a year ago, in an experimental group in Massachusetts, they contacted us to synthesize, that they want to synthesize this material based on our previous publications. And they do really synthesize it, and then they verify our predictions in experimental paper. And that was this paper that published this year in 2021. We also collaborated with this work because we need to calculate some more to improve our computations than the previously published work. Now, I will quickly review another methodology to enhance optical absorptions. Now, one of the reasons I mentioned before, that even at minimum gap, optical absorption can be prohibited. For example, this is another structure which is called Delaphosite structure, copper yttrium oxide. The blue again are copper, red are oxygen. These greenish atoms are the yttrium. So this is like a layered structure, as you can see. And this is a band structure. This is rather high band gap, almost 3 electron volt. And if we see exactly at the lowest gap, this is again optical absorption probability. Exactly at the lowest gap, absorption is exactly 0. So no absorption at the lower energy range. And again, this absorption is 0 because it is prohibited. The electron transition from the valence band to the conduction band at this point is prohibited due to some dipole selection rules. Now, those dipole selection rules are basically imposed by the symmetry of the crystal. So the idea of this work, let's break the symmetry. If we break the symmetry, then we should see non-zero absorption around this place. And this is what we did. Now, to break the symmetry, again, we alloy it with some isovalent atom, which is gallium. Now, one layer is yttrium, one layer is gallium, another layer is again yttrium. Because one layer is substituted by a different atom, the crystalline symmetry at a larger scale is now broken. As it is broken, the gap, as you can see, where the minimum gap, the absorption was 0, now we do have some non-zero absorption. As an added benefit, even the gap gets smaller now. So not only we get non-zero absorption at previously 0 absorption point, but also the gap is reduced. So this is another way to increase absorption simply from the crystal symmetry point of view. Now, there are several configurations that we considered, and these are the absorption plots. It is just shown here for convenience. This is the original copper yttrium oxide, where the absorption was forbidden at the smallest gap. Now, when we do all these alloying, different configuration for yttrium, one configuration with indium, all these has significantly lower absorption onset. And this work was published in Applied Physics Letter in 2009. It's a rather older work, but these results actually was important for us when we mentioned the alloying methodology on tungsten oxide. This consideration, that symmetry breaking consideration, was implicit in there. So now I will be making some concluding remarks. We hope that we're not yet too late to curb the global warming. We should start as soon as possible. We should not wait for somebody else to do it. Of course, we need to cut down the fossil fuels, all the petroleum, natural gas, coal. These are the contributing factor for the greenhouse gases, as we call them, in the atmosphere. And we should increase the deployment of renewable and sustainable energy sources as in an emergency basis. Now, we also mentioned that solar energy holds the utmost promise to power the entire planet Earth because there is plenty of solar energy. And the more than that we may be able to use in next few thousand years. One of the major challenge for utilizing or deploying solar energy is a material challenge to have a better, efficient material that can absorb and conduct electrons, like absorb light and conduct photoelectrons. The material challenges includes, for example, discovering new materials with efficient light absorptions, good carrier mobility, conduction, and overall stability. The stability is important because this kind of solar energy devices probably will be sitting in open environment. So it should withstand those whatever harsh weather condition in outside. And finally, for doing all these things to tackle the material challenge, this leads us to do fundamental research in physics, because we are basically considering what happens when electrons are interacting with each other. What happens when electrons are interacting, or let's say that when temperature increases. So this really point us, and this is where we started our work, at least, starting from basic condensed matter physics, and then see what we can do to contribute to the betterment of global environment. Finally, so that's basically the end of my technical presentation. Finally, I would like to acknowledge some of my teachers. I think I need to do that. Professor Haruna Rashid and Professor Lalit Mohan Nath. When I was a student at Dhaka University, these two scholars not only helped me, I think they changed my attitude in academia, taught me from the beginning physics and research in physics. And then when I joined Rajshahi University as a lecturer, Professor Arun Kumar Bosak, he was generous enough to take me in his group and initiated my research as a professional physicist in a professional environment. Despite the barrier we face, let's say in universities, in a professional level, and you know the barriers in environment like in Rajshahi or in any place in Bangladesh, how to overcome those barriers, how to focus on the work. I am really indebted to Dr. Arun Kumar Bosak to teach me or to help me to understand those barriers and overcome those barriers to do research with him. And finally, I would like to acknowledge, even though he was not a direct teacher for me, but I was fortunate enough to spend some time with Professor Jamal Nazrul Islam. He made me a basically hardworking person. I understood from all of them, but especially from Dr. Islam. He once told me, I still remember this quote. He said that read something. If you don't understand, read 100 times. If you don't understand, read 1,000 times. Keep reading till you understand that thing. That's a metaphorical statement. However, that changed my outlook of doing things. Everything is difficult till I understand it. We need to spend time to make sure that we understand stuff. If we don't understand whatever we are doing, we'll not be able to contribute much. So these are my 4 teachers. I definitely want to acknowledge them and would like to honor them. Among them, Lorita Mohan Nath and Professor Islam, they passed away. And still Haruna Rashid, he's very not very well, his health. And I have not direct communication with Dr. Boshak for some time. I would like to get back in touch with him. Now, finally, I would like to acknowledge my group member, my research group member. This photo was taken just before COVID. We went for a group lunch. So these are the people who basically do the work. I just take credit from them. So thank you very much for your patience listening to me. If you have questions or comments, I will be happy to take questions and comments. Thank you.
Thank you, sir, for your wonderful presentation. So last time when Dr. Khairul Alam Khan sir talking, his connection was lost. So I'd like to welcome him again. Sir.
Dr. Pretam. Thank you very much, Muhammad Huda, for a nice presentation on very important topics in present Environmental Day, that is World Environmental Day. Really, it's tough work for anybody from Bangladesh. You know, you have a computer, but here we are suffering from a simple computer. We have no simple computer at all in our laboratory sufficiently. Although some of our colleagues is working hard with your first principle, ABT, DFT first principle, and one of our researchers, Dr. Aptabuzzaman, has published one of his papers from Japan. When he was in Japan, he published a paper in scientific report also. And they're working from here. They're publishing in Springer journals, in Journal of Scientific also. Here, our researcher, and to introduce you, Dr. Russell. He is working with a very important topics, photovoltaic cell for solar energy. I hope he will do a lot in future. And our host, Dr. Pretam Kumar Das, is directly research student of Dr. Arun Kumar Boshak. It's a pleasure for all of us, and he is very hardworking person. আমি বাংলায় কিছু বলতে চাচ্ছি যে আপনার যে অপটিক্যাল অ্যাবজর্পশন এনহ্যান্সমেন্টের যে প্রজেক্ট, সেই প্রজেক্টটি আরো সাফল্য লাভ করুক। ধন্যবাদ। এবং আপনি দেখিয়েছেন যে 2 ইলেকট্রন ভোল্টের নিচে নিয়ারলি 1.7 ইলেকট্রন ভোল্টে আপনি আপনার ইজেকশন অফ ইলেকট্রন পাচ্ছেন, এবং এই অপটিক্যাল অ্যাবজর্পশন যদি আমরা আরো বেশি পাই তাহলে সোলার এনার্জি আমরা বেশি পাবো। বেশি পেলে আমাদের এনভায়রনমেন্টটা সাস্টেনেবল হবে, এই প্রত্যাশা রাখছি। এবং ফিজিক্স ইন ডিফারেন্ট ওয়েতে এনভায়রনমেন্টাল সাস্টেনেবল কাজ করছে, আপনি কতগুলো ব্রাঞ্চ অলরেডি দেখিয়েছেন। এর সঙ্গে আমরা আরেকটা ব্রাঞ্চ আমি যোগ করতে চাই। আপনি নিশ্চয়ই অবগত আছেন যে আমাদের ফিউশন প্লাজমা ইজ অলসো a very present focus on environment friendly energy resource. And okay, all right. Thank you very much
ধন্যবাদ, আপনাকে অসংখ্য ধন্যবাদ
for giving the time to us.
আপনার সুন্দর কমেন্টের জন্য অসংখ্য ধন্যবাদ।
অনেক ধন্যবাদ স্যার। আমাদের সাথে ডক্টর শেখ রাসেল আল আহমেদ স্যার আছে। স্যারের যদি কোনো কমেন্ট থাকে, যেহেতু আমি জানি, যতটুকু জানি স্যারও এই বিষয়ে কাজ করছেন এবং রিসেন্টলি স্যারের একটা পাবলিকেশন হয়েছে সোলার সেলের উপরে। তো স্যারের যদি কোনো কথা থাকে বা কোনো প্রশ্ন থাকে এই আমাদের আজকের স্পিকারের কাছে।
আপনি মিউটেড, আপনি যদি ডক্টর আহমেদ প্লিজ।
সর্বপ্রথমে স্যারকে অসংখ্য ধন্যবাদ স্যারের এই মনোমুগ্ধকর প্রেজেন্টেশন প্রদানের জন্য।
আপনাকেও ধন্যবাদ।
তো আমি একটু মানে কয়েকটা বিষয় একটু স্যারকে মানে স্যারের কাছে জানতে চাচ্ছিলাম।
প্লিজ।
সেটা হচ্ছে যে কপার বিসমথ টাংস্টেন অক্সাইড যেটা স্যার আপনি মানে প্রেজেন্ট করলেন, এই অ্যাবজর্পশন যেটা ঘটছে এবং 1.5 যে এনার্জির নিচে অ্যাবজর্পশন মানে পাওয়ার ক্ষেত্রে আপনাদের
অ্যাপ্রক্সিমেটলি 1.5 জি।
আচ্ছা, তো এটা যদি আমরা 1.3 এই রেঞ্জে পেতে চাই, তাহলে নেক্সট রিকমেন্ডেশন বা নেক্সট কোনো কাজ করছেন কিনা বা করবেন কিনা?
জি, মানে যখন আমরা অ্যালয় তৈরি করি, then it's become its own crystal, right? নিজে একটা crystal structure. So now we can start from there. We can start from there and then probably dope to reduce the gap. Now, আমি পার্সোনালি আমার পার্সোনাল এক্সপেরিয়েন্স থেকে আমি যতদূর জানি, আমি এক্সপেরিমেন্টাল সায়েন্টিস্টদের সাথে ক্লোজলি কোলাবোরেট করি। সো যেটা হয়, ডোপিং স্ট্র্যাটেজিতে ওই চার্জ ডিফেক্ট তৈরি হলে ক্রিস্টালিনিটি ভালো থাকে না। তো আমি ডোপিং সাধারণত করতে চাই না, যদিও ডোপিং করতে হয় বিকজ ফর আদার পারপাসেস, টু স্টাডি আদার প্রপার্টিজ অফ মেটেরিয়াল। নাও যেটা ফর দিস বিসমথ কপার টাংস্টেন অক্সাইড, এই প্রজেক্টে এই অ্যালয়িং স্কিমে উই হ্যাভ অ্যাকচুয়ালি another publication which was published in 2016 or 17 in Applied Physics Letters. ওটাকে আমরা বলি CTTO, copper tin tungsten oxide. Copper tin tungsten oxide, that alloy has even lower band gap than 1.5. That start absorbing at lower gap. For example, in silicon, even though its gap is 1.1 electron volt, কিন্তু সিলিকনে 1.1 ইলেকট্রন ভোল্টে অ্যাবজর্ব হয় না, কারণ ওটা হচ্ছে ইনডিরেক্ট গ্যাপ। ডিরেক্ট গ্যাপ একটু বেশি এবং ইনডিরেক্ট গ্যাপ মেটেরিয়াল গুলোর একটা প্রবলেম হচ্ছে যে সার্টেন ট্রানজিশন ইজ মেডিয়েটেড বাই ফোননস, ওখানে কিছু এনার্জি লস্ট হয়। সো when we predict alloy, we also want to try to make sure that this is an indirect gap material, this is a direct gap material, not an indirect gap material. In that case, the later work which we published on CTTO, copper tin tungsten oxide, was even better than this copper bismuth tungsten oxide. The reason I presented copper bismuth tungsten oxide, because after we predict everything, theoretical prediction, not only that, theoretically we also predicted the synthesis route to synthesize this material. And based on our prediction, this experimental group in University of Massachusetts, it's in the state of Massachusetts, it's a Worcester Polytechnic Institute. A scientist from there, he proposed that he want to synthesize it. And they synthesized it, they measured the properties, compared it with our theoretical results. It was such a good match that it published just this year in a Royal Society journal. Hence, I decided to present this because this is thoroughly experimentally verified. The other one, CTTO, there are at least a lab is trying to work on it. We will see if they can synthesize it and measure some properties. Then we will compare it.
স্যার, তো তাহলে আমরা ধরে বলতে পারি যে যেহেতু 1.5 ইলেকট্রন ভোল্ট nearly you have achieved, so it can be used in thin film solar cell.
Yes, thin film solar cell এর একটা important factor হচ্ছে যে like gallium, indium, like CIGS, right? Copper, indium, gallium sulfide or selenide, ওগুলো বেসিক্যালি থিন ফিল্ম সোলার সেল হিসেবে ইউজ হয় কারণ ওদের absorption coefficient is very high. So only a thin layer is needed to absorb significant light. Now for the one I have shown today that really have very high absorption coefficient from let's say 1.5 to 2 to 2.5 electron volt. This can be used as a thin film. In fact, the experimental paper that was published, it is a relative, not exactly the ultra thin film, but it was a thin film. As long as the absorption is very high, then silicon cannot be used as thin film because of the indirect gap. Its absorption is not very high.
স্যার লাস্ট একটা কথা, আমি আরো অনেককে হয়তো ফ্লোর দিতে হবে। ডিফেক্ট লেভেল কেমন পেয়েছিলেন?
Defect level.
জি জি।
Okay, for copper, bismuth, tungsten oxide, from our theoretical presentation or work, the major defect is copper vacancy. And the copper vacancy in this kind of material is preferable, and it happens spontaneously. That means defect formation is favorable. Because of the copper vacancy, this material has p-type conduction. So this is a p-type metal oxide. P-type metal oxide is desirable because there are not many oxides that are naturally p-type. So this is one of the material, this copper, bismuth, tungsten oxide, which is naturally a p-type material because of copper vacancy formation. And the concentration of copper vacancy is not too much to make it a degenerate semiconductor. That means it is, I think, I don't remember the number, it's something like 10 to the power 14 per centimeter cube. It's just the number based on experiment.
It's so 10 to the power 14 per cubic centimeter. Maybe it is really good achievement because such a low level of density is really difficult to produce in experimentally.
Yeah, I think
it is good achievement.
I hope so because the group worked on this. They're very good group.
Thank you, sir. Thank you very much for your.
You're most welcome.
থ্যাংক ইউ স্যার। আমাদের আরো কিছু প্রশ্ন আছে ইনবক্স এবং কমেন্টে। আমি ইনবক্সে প্রশ্নটা নিচ্ছি যে হোয়াট ইজ দ্য মেইন ডিফারেন্স বিটুইন Hartree-Fock and DFT?
Okay, so methodology wise, Hartree-Fock theory is like a wave function based theory. For example, if we take quantum mechanics, the central equation of quantum mechanics is Schrodinger equation. And when we solve for Schrodinger equation, we get a solution for a wave function and energy eigenvalues. Hartree-Fock is a similar theory. Now, the difference between Schrodinger equation and Hartree-Fock equation is that in Schrodinger equation, if we want to solve for, let's say, 10 electrons, we solve for 10 electrons with a potential term in the Schrodinger Hamiltonian. Now, that term will have explicit electron-electron interactions. Those kind of electron-electron interaction can make solution for a Schrodinger equation very, very difficult. I would say almost impossible. What Hartree-Fock does is that it considers one electron moving in the field of rest of the electron. So let's say if there are 10 electrons, one electron is moving in a potential field created by the other 9 electrons. So other 9 electrons, they create a background static mean potential. So it's basically a mean field theory. In that mean potential, electron moves, and each of the electrons' wave function is solved in this model. So this is basically the Hartree-Fock model. Now, in the density functional theory, the wave function is not considered to start with. What it says that if we know the electron density, the ground state electron density, and it can be known by doing computation, or it can be simply measured in experiment. Electron density is an observable quantity. If we know the electron density, then we can formulate a theory and can solve a quantum mechanical equation that almost look like a Schrodinger equation, but not exactly a Schrodinger equation. That equation is called Kohn-Sham equation. When you solve this, we basically solve for the electron density. So this is the main difference. One is purely wave function based, another is density based. And if we remember that undergraduate quantum mechanics, the electron density is basically mod square of the wave function times the electronic charge. So electron density can be found either by calculation or from experiment.
Yeah, thank you, sir. We have another question. So, as we know that the efficiency of solar system is less, so can we get our required energy demand from solar cell?
Yes, of course. Now, if I go to the more technical side, for example, the kind of photograph or the diagram I showed for silicon photovoltaic with like a PN junction kind of photovoltaic, a single junction solar cell. A single junction solar cell has a maximum theoretical efficiency around 31 to 32%. That means whatever we do thermodynamically, we cannot go over that 32%. The best possible single junction cell will give that efficiency. Now, there are cells that goes close to that 30%. For example, cell based on gallium arsenide. That goes close to 30%. But again, we cannot go beyond that. What to do to go beyond that? We can make multi-junction solar cell. 2 junctions, 3 junctions. Now, experimentally, in the lab at least, it has been shown that those multi-junction solar cells have higher efficiency, more than 50% efficiency even. Now, here is the point. Let's say, for argument's sake, we're talking about a very simplified single junction solar cell, a solar cell like the typical solar cell we have either in silicon or cadmium telluride. Now, another interesting fact about solar cell is that cadmium telluride is basically one of the most successful commercially available solar cell that is deployed in India, basically, because there are words from Indian industry and the scientific community that in the environment, like in India, similar in Bangladesh, cadmium telluride based solar cell works better. Anyway, let's say that in average, they have efficiency around 20%. So 20% efficiency. Now, what we said that, or it's a fact, the sunlight that strikes Earth in an hour, that can power up the whole planet for a whole year. So that means we have enough sunlight to work with. Even if we use 1 out of 10, like 10% of the sunlight, or even 5%, that is more than enough to power the whole planet. So yes, even in 20% solar cell, or 20% efficiency solar cell, it is possible to power up the planet. Now, what is the arguments against it? The arguments against it, especially in here, as we know, is that is solar cell expensive? Yes, solar cell to start with can be expensive, but the stability once you install solar panel could be up to 30 years with minimum maintenance. That pays by itself. And because of technological improvement in last 40, 50 years, nowadays solar cells are not expensive. These are becoming cheaper. And most likely when we talk about solar cell, we are not talking putting solar panels on the roof. Yes, that is very helpful, but there could be a huge industrial solar farm where they will produce solar electricity or photovoltaic electricity. And 2 years ago, in USA, there is a funding agency, government agency, which is called National Science Foundation. They organize a meeting with the industry partner or with photovoltaic industries. So I was invited in that meeting. I have found some of the CEOs of those photovoltaic industries. They were saying they can sell electricity at a cheaper rate than the traditional electricity we get. Traditional electricity can come from, at least in Texas, it comes from what do you call it, the coal-based plant, another is wind-based plant, and of course the natural gas-based plant. And probably 10 to 15% of the power we get is from nuclear plant. So with all this traditional power form, they said that they can supply electricity at a lower cost. It's just that government regulation is not allowing them to do so. So even at the present state of technology, the solar electricity can be cheaper. The technology is implementable anywhere in the world, and there is enough sunlight. The only problem is at the night, but we can either preserve or store the sunlight by producing hydrogen, save the hydrogen, use it as a fuel in the nighttime, or save the electricity in battery. The battery technology has improved a lot. So those intermittent problem, when the sunlight is not available, the electricity can be stored, or, for example, we have wind energy, which is significant enough in many places on Earth.
Thank you, sir. This may be the last question. So, what does the different points Z, Y, X, W, etc. of the horizontal axis of the band diagram represent?
Oh, those are for the optical absorptions. Can I go back to one of my slides?
Yes.
Let me go there, pick up a better figure. Probably this one should be fine enough. No, not this one. I think I want to show a crystal structure. This one probably, yep. I think this should be fine. Let me bring up everything. This XYZ are basically absorption along x-axis, absorption along y, absorption along z. This X, Y, Z are related to the crystalline orientation of A-axis, B-axis, and the C-axis. Here the C-axis is just perpendicular out of the computer screen. So when we say this X, Y, Z, these are basically either you can say that polarization along A, B, and C, or just absorption along A, B, and C axis of the crystal lattices. One of the reason I separate them, most of the time in publications or when we publish, we don't show three lines separately. Rather, we make an average absorption or a combined vector absorption, like x square plus y square plus z square square root. That's what we do, and then publish that one line to show the optical absorption. That gives a pretty much a good idea of what's happening. Here I separate them to show the anisotropy of the absorption. That means the absorption along A, B, and C are not same, which basically another way of saying the crystal symmetry along A, B, and C are not same. Atomic arrangements are not same. And as I mentioned, this structure, or even tungsten oxide itself is a distorted perovskite structure. That means it's not exactly symmetric cubic perovskite. Similarly, this is also a scheelite structure, but a distorted scheelite structure. Hence, the cubic symmetries that those could have been there is broken. That created this anisotropy in absorption in three different lattice directions.
Thank you, sir. As we don't have any more questions, so we can conclude our discussion session. So this is a great webinar for our student, and as this is the Environmental Day, World Environmental Day, so this is a special webinar, and we try to focus on environment-friendly energy source. So as you know, the fossil fuel we are using most in now on dependent on fossil fuel, and it emits a greenhouse gas and carbon dioxide, so that has a bad effect on environment. So we have to go renewable energy, and I think if we go this solar cell, as you mentioned, that we can fulfill our demand. So I think those who are watching this program and some of our students and the viewers will feel interested in doing research in this field, and maybe in near future we'll find some better option that some industry will formed in our country so that we can find our demanded energy from solar cell or some renewable energy. Thanks again for helping us to arrange such an important webinar. Yeah, and thanks Sheikh Rasul Ahmed sir and Dr. MD Khairul Alam sir for joining with us, for helping us, for encouraging us, for arranging continuously a series of webinars. So thanks again.
Thank you also for inviting us. Thank you.
No, thank you. And just আমি শেষ করতে চাই একটা comment. এটা হচ্ছে যে if you have any questions regarding what I presented today, or anything on the subject, please feel free to email me, and also for the students and the faculties in here. If you think that a research collaboration might help,
yeah,
I will be happy to do as much as I can. The computational power is definitely a big problem. I need to explore, I think, because I have Indian collaboration from IITs in different universities. They do have significant computing power over there. I think in Bangladesh it is possible to build probably not a big computing center, but a small cluster which can do this kind of calculations.
Yeah, so, and thanks for inviting to be a collaborator of yours. So I think some of our researchers and our colleagues and our students will definitely,
especially the students, if they have questions. I like to talk with the students. I will be very happy to even talk, let's say via Zoom, if somebody wants to talk with me.
Yeah,
feel free to give my information to who wants it.
Yeah, of course, sir. Then I'll arrange a general talk with the student later.
If I have time, or of course I will make time. I will be happy to talk with the students.
And when you come in, so come next time Bangladesh, so then please inform us. Then we can invite you for a face-to-face session after the COVID. Definitely,
thank you very much.
As we know that,
I will definitely have a visit because I'm মানে আমার নানার বাসা রাজশাহীতে, দাদার বাসা দিনাজপুরে. So I know the area very well.
তাহলে তো আপনাকে আমাদের উপর দিয়ে যেতে হবে। সো আমরা ডেফিনেটলি আপনাকে পাবো। সো ধন্যবাদ স্যার আমাদেরকে এত সুন্দর একটা ওয়েবিনার করার সুযোগ দেওয়ার জন্য, এবং আশা করব আমরা আপনাকে আবার আমাদের পাশে পাবো, এবং শুধু ওয়েবিনার না, আমরা আমাদের গবেষণা প্লাস আমাদের ছাত্র শিক্ষক যারা আসলে কোলাবোরেশন করতে চায় এবং অ্যাজ এ উপদেষ্টা হিসেবেও আমরা আপনাকে পাবো সবসময়। আমাদের ধন্যবাদ স্যার, ভালো থাকবেন, সুস্থ থাকবেন, এইভাবে আমাদের সাথে আপনার জ্ঞান শেয়ার করে যাবেন।
Thank you. And also Dr. Ahmed and Dr. Alam, thank you very much for being here and nice comments. Thank you very much.
Thank you sir, and you are most welcome. Assalamu alaikum.
দেখা হবে কোন এক সময়।
জি স্যার, আসসালামু আলাইকুম স্যার।